Welcome back to the Spectral Edge. Today we're diving into a thought experiment that sounds like science fiction, but it actually grounded in the hardest physics we know. You've all seen photos of the auroras, those shimmering green and red curtains dancing across the polar skies. We usually describe it as a light show, but if you talk to an RF engineer, they'll tell you something different. They'll tell you an aurora is actually a planet-sized intermodulation event, a massive down conversion of solar energy hitting the Earth's mixer and spitting out a product in the visible spectrum. It's a wild way to look at it. The sun sends out this broadband signal of charged particles, the solar winds, and it hits our magnetosphere. That magnetic field acts like a giant waveguide, funneling those particles into the ionosphere. When they collide with oxygen and nitrogen, they pump those atoms to a higher energy state. When atoms relax, they release photons. Essentially, the universe is taking high energy kinetic and electromagnetic interference and mixing it down until it hits 400 to 800 terahertz range, that tiny reality our eyes can actually see. So the billion-dollar question that we're asking today is, if nature can do this with solar wind, why haven't we engineered a way to see our own radio signals? Why can't I put on a pair of glasses and see the Wi-Fi in the room? See the 800 cellular band as shimmering red curtains draping over the city. We're living in a soup of electromagnetic information, but to us, the room looks empty. If we can see the sun's inner mud products, why can't we see the ones coming from our own cell towers? The problem, as always in engineering, comes down to link budget, specifically the energy of a single photon. A visible light photon, like the green ones in the aurora, has about 2 electron volts of energy. Compare that to a radio photons at 800 megahertz, which has about 3 millionth of the electron volt. To bridge that gap, we need to gain roughly 58 decibels. Now, 58 decibels is an easy benchtop for an amplifier, but you can't just amplify a photon into a different color without nonlinear medium to do the heavy lifting. Now, that's where engineering gets tricky. In the aurora, the medium in the upper atmosphere. In the lab, we use things like nonlinear crystals or phosphorus screens. Think about old-school cathode ray TV tubes. Those were essentially contained auroras. You had an electron gun, the solar wind hitting the phosphorus screen, the atmosphere, and creating the light. But to do that for the ambient RF, the signals are so weak that the thermal noise in the room, the little heat in the air, would drown out the signal before you could even see it. At the room temperature, the atoms in the RF goggles are vibrating with more energy than the radio waves we're trying to detect. It's like trying to hear a whisper in the middle of a hurricane. To actually see RF the way we see auroras, we'd need to cryogenically cool our sensors to near absolute zero just to get the signal-to-noise ratio high enough to distinguish a cell signal from the background heat of your own body. It's a thermal nightmare. But we're getting closer through digital bridges. We're seeing a rise of software-defined radios paired with augmented reality. We can now take a high-speed ADC, run a fast Fourier transfer to find those intermod products and then paint them onto the AR display. It's not a physical upconversion of the photon, but as a result is the same of the engineered auroras. Let's talk about the server rooms and see the interference patterns as they glow clouds of light. We're finally building the eyes that nature didn't give us with the SDR. It changes the way we think about the invisible. If we could see 100 megahertz band, we wouldn't see the clean lines. We would see the ghosts of intermodulation. The formulas, the 2F minus 1 and others, products, appearing as a flickering streaks whenever the two signals gets too close. we would realize that our world isn't just filled with signals, it's filled with the beautiful chaotic interactions between them. The aurora isn't just a miracle in the sky, it's a blueprint for the next century of spectral engineering.